Welcome back to TTV. In the last video, we looked at functional dependencies and the types of functional dependencies that we call full and partial functional dependencies. We talked about them with examples, and I told you in this video we will be looking at the reasoning behind functional dependencies. Let's dive right in. Behind FTs. Reasoning behind FTs. Well, now I'm going to introduce you some of the notations that we are going to use in the future videos. So first of all, whenever we are presented with a relation, let's say there is a relation, R with several FTs, with several FTs, with several FTs. These initial FTs, actually imply more logical FTs. More logical FTs. Well, for example, if you have student code, student ID, student name, and if you have student age, well, there is a basic FT that we can simply say stud ID functionally determines stud age. We can say that. Let's say X is equals to stud ID and Y is equals to stud age. Well, X functionally determines Y. But if I said Z is equals to stud ID, comma stud name, Z functionally determines Y is actually a functional dependency. Even though it is a partial functional dependency, it still is a functional dependency. Now, you can see that this is the initial FD that we had, but there are also other possible functional dependencies. And if we derive these functional dependencies from the initial FDs, we will be left with a set of initial FDs and also derived FDs. After deriving these implied FDs, we will have a set of initial FDs and derived FDs. Initial FDs have the notation F. Derived FDs don't actually have a notation, just keep that they are also a set. That can also be inside a set. That is a different set, okay? I'm not talking about the attributes. I'm talking about the FD set. We can put FD into sets, right? Different FDs into sets. So if you add these two, F plus derived FDs, you will be left with another set of FD, and that FD is called as closure. And the notation for closure is F plus. Okay, so from a given set of FDs, F, you can derive FDs, and the total union of derived FDs as well as initial FDs is called the closure. And that is named as F plus. All right. So in the last class, I told you that we have inferral methods to come up with FDs. So that's the thing here. To compute F plus, we need inferal methods. One of the famous inferal method is called Armstrong's Armstrong's Axioms. And this is a very sound and complete method to find out all the derived FTs in F plus. Okay, this is the best way to find out all the FTs in F plus FT set. All right. So this is the reasoning behind FTs. The reasoning we use to find out what are the possible FTs in F plus. Now I will introduce you why Armstrong's axioms Armstrong's axioms are sound and complete. First of all, we will look at its soundness. Okay, I'm just making this easier for everyone. That's why I'm teaching this. Soundness means you all know soundness means it's correct, and complete means it complete. Completeness means it's complete. All right, that's the basic idea. But I want to make sure this is not ambiguous to anyone. That's all. All right. So soundness. Armstrong's axioms don't generate erroneous FTs. All right. It doesn't generate erroneous dependencies or FTs. That's very important that we must keep in mind. Armstrong's axioms are direct, straightforward, and when you use them, you won't be generating any erroneous FTs. So when you apply when you apply Armstrong's axioms when you apply Armstrong's axioms to an initial set of FTs, which is called as capital F or uppercase F. The resulting set F plus that are logically implied by the initial FT will only contain correct FTs. All right. So this FTs in F plus will be consistent with initial set of FTs. That's what we mean by soundness of Armstrong's axioms. I will explain it again. When you apply Armstrong's axioms to an initial set of FTs, the derived FTs will be only implied by F, and they will be included in F plus. Which means any FD in F plus will be consistent with F. Now that is soundness. Now we will talk about completeness. All right. If you apply Armstrong's axioms again and again on the initial set of FDs, you will finally, at some point, you will generate all the possible FDs that are implied by the initial FDs. So every FDs that are possible can be derived by using Armstrong's axioms. I will come again. When applied repeatedly, you will generate all the implied FTs of initial FTs or F. All right. So every FD in F plus can be generated and included and included. This is why we normally use Armstrong's axiom. Now let's go to another important section. Now I will introduce you to the basic Armstrong's axioms. The three basic Armstrong's axioms. First one, reflexivity. Is it reflexivity? It's reflexivity. Yeah, reflexivity. Second one, augmentation. Third one, we have transitivity. Reflexivity states that if any set of attributes, sorry, it's not about attributes, obviously, this is about uh, FDs. Yeah, this is about FDs. And even though we speak about FDs here, the first and foremost rule, reflexivity, states that if Y is a subset of X, if Y is a subset of X, X functionally determines Y. If Y is a subset of X, X functionally determines Y. X functionally determines Y is always true. Is always true. Is always true. Augmentation rule, augmentation axiom, states that if X functionally determines Y, XZ functionally determines YZ. In relational algebra, I taught you some operations. In that, union was one of the operations. XZ can be interpreted as X union Z, and YZ can be interpreted as Y union Z. You may ask and you may have some questions like, in logical operation, didn't you say, according to logic gates, didn't you say XZ is X and C? Didn't you say that? How can be this X or? Because we know or usually correspond to union, and corresponds to intersection. But in relational algebra, I don't know why the mathematicians do this. I really don't know. But this is the notation they are using. Okay, this is the notation you are using. I can't do anything about that. And for intersection, you won't believe me. X comma Z is represented as X intersection Z. Seriously, I don't know why they did this. So yeah, I don't know why, but this is the second axiom. So that's it. And we have the third one, transitivity. This is more of a like a differentiation chain rule. Okay, it's just chains. If X functionally determines Y and Y functionally determines Z, we can say X functionally determines Z. We can say if these two conditions are met, this conclusion can be derived from that. And also like this, if X functionally determines Y, XZ functionally determines YZ. All right. These are the basic Armstrong's axioms. In the next video, we will dive deep into reflexivity, augmentation, and transitivity. I don't think this will take too much time, since already this is pre-explained. I think this won't take much time. If it does, we'll do some examples and learn. But in the next video, we will be looking at three basic Armstrong's axioms deeper. Thank you for exploring closure of functional dependencies and Armstrong's axioms with us. If you enjoyed this video, give it a like and share it with others. Subscribe and click the notification bell to stay updated with the latest lessons in this series. I'll see you in the next video. Until then, keep learning and stay curious. Bye bye.